somehow they're not much different. I believe, maybe it's very depending on the size of the cleat, the number of cleats, and the length of the cleat. So it's hard to control, but somehow we compare to the other standard strapper shoes, and the level was very similar. And we also measured some free moment, and also it showed some trend, and then for TRX, strapper shoes has showed high free moments. And this is from the human testing, and we are looking at the ankle and reduction moment. And there are a little bit difference higher compared to the running shoes. And when you look at the external rotation moment, there are differences between stopper shoes and running shoes, but also there are a little bit of difference between among the stopper shoes as well. So it was kind of we look at the mechanical aspect and human aspect from the testing, and we see that translational and rotational traction tests show a difference. It's obvious because it's a tree. It's not like it's not round. There's some trees that have some blade type. So also there are some distinct differences in chill and human testing. So we can see the different aspects. And so, but we found that the general findings here at the faculty design change the traction test weeks and moments. So when we summarize the result, translation traction, you can see TRX has a greater than the running shoes and other stopper shoes, but rotational traction, there are not much differences between among stopper shoes. So which means that TRX shows the higher translational traction, but the rotational traction is the same as the other stopper shoes. Which means that when we said, I was kind of simply believe translational traction is important to run fast in this direction. But rotational says if the cleat is stuck on the ground, you might have a little bit of rotational loading at the knee. So I say maybe not good. So we kind of got some little bit of piece of idea that the new design maybe it's okay. Higher translational traction and the same level of the rotational traction. So and then we look at some rotational joint moment. But the human testing it doesn't show like the same trend from the mechanical testing. I believe it's a human adaptation. So human change the little movement depending on the condition. So it's good to understand, like from the mechanical information when you apply to the human life. So in this project, I was working with Brett Anderson and others, and Ben Lee was interested in this project, and also the shoe was provided by Divas. And then later, I was doing my own PhD work, and it's a little bit different direction. It's very complicated, because I think it was very challenging. So when I do PhD, so I had a lot of hard time. So also I had to work with some other people like medical doctors and biologists, and then to understand the whole big picture in this injury. So I was studying the female AC injury, and then the subtitle here is alternations in knee joint left knee in the menstrual cycle. They change the muscle activation patterns during the athletic movement. So let's change the topic here. The anterior cruciate ligament is one of four major ligaments at the knee. It connects from the posterior lateral part of the femur to the anterior medial part of the tibia. And this attachment allows to register anterior translation of the tibia in relation to the femur. So it is very important piece in the body. So most ACL injuries in sports occur during the non-contact situation, and ACL injury mechanism in non-contact situation often associated with sudden deceleration and change in the direction, such as cutting maneuvers. It's been known that the female ACL injuries occur 2 to 8 times more frequently than the male counterparts. So it's still an issue. Everybody wants to understand why females are more injured. Because the females, they're more active to participate in the sport these days. But it seems they seem to have they're more injured. So, but the most current studies, they haven't studied ACL injury mechanisms in females by considering gender differences in anatomical and biomechanical and hormonal factors. However, it is like a gender difference alone is not sufficient to explain the variability in injuries among females. Since not all females they got injured, since not all females are prone to greater gender-related risk factors, and they're injuring the ACL, it seems a more complicated ACL injury mechanism are in place. So this is my proposed female ACL injury mechanism, and the few studies they suggest a certain phase of the menstrual cycle may be related to a high instance of ACL injuries. It's more like epidemiology studies. They look at the number of injuries in a certain time, and they speculate what's going on. But it's been known that during loading, it increases strain on the ACL, therefore tears the ligament. Loading and injury is known there is some relationship. And few studies they investigate a certain phase of the menstrual cycle is related to the kind of biomechanical risk factors, including joint loading or muscle activations. But their findings are very controversial, so it's not clear. And recent studies suggest greater medial joint laxity in female may decrease joint function and therefore contribute to more instances of ACL injuries in sports activity. And also some studies, they found the increase in medial laxity or joint laxity in the certain phase of the menstrual cycle. However, how change in joint laxity during the menstrual cycle also affected the biomechanical risk factors like the joint loading and muscle activations, which lead ACL injuries has not been well investigated. Therefore, the current study was intended to study the links between joint laxity and biomechanical risk factors, especially here joint loading and muscle activation patterns, as a potential ACL injury mechanism in females. So in the previous study, we published a couple papers in a medical journal, and we found similar to the previous study, we found some increases during laxity during ovulation, and we believe there are some hormonal effect on the joint laxity. When we say joint laxity, it's a passive overall general laxity, but we also expecting some ligament might be relaxed in passive situation. However, when we compare this loading change across the menstrual phase and among the female, we don't see any kind of trend. We are expecting maybe there are increase of joint laxity during the certain menstrual cycle. Maybe also they are changing something. So we are looking at the general trend. But when you look at, it wasn't there. But when we carefully look at the individual change or more details, and we found higher major laxity will relate to higher individual loading. So I think there is something going on. However, it is still unknown whether alterations in joint laxity are also associated with changes in muscle activation. When you say muscle activation here, I'm saying the onset of muscle activation or contraction patterns between muscle pairs during some athletic movements. So for the testing, we recruited 26 healthy females. They're young and healthy, and they have a normal hormonal cycle. And then The purpose of the study was whether a change major laxity during the menstrual cycle has influence on different muscular controls of the lower extremity. And we are looking at the time of effect by their phase. Also, we look at whether subject variations in major laxity is linked to muscle activation patterns. So we kind of look at the more detail and looking at the effect of the laxity in individual levels. So this is the cycle, and this is our three measurements. And you see that the estradiol changes and progesterone changes over the cycle. And we took the blood samples, and then we measured the during laxity. After the measurement, we asked the subject to participate in biomechanical testing. So we did some biomechanical measurement. We do some cutting maneuvers at certain speed. We place the EMG and we place the markers. So subject has to come at least 3 times to over the cycle. So when you look at the onset of muscle activation, so it's a little bit hard to work with the EMG. It took me quite a long time to figure it out because of sometimes we have a noise, and also the pattern, the size of the signal is very challenging. So somehow I did some coding, and then so we define onset of the muscle activation when the signal is greater than 3 standard deviation of the EMG signal, and this is a window. This is a hip contact. This is a ground reaction force. We are expecting some onset of pre-activation of the EMG before the hip contact. So also I look at some co-contraction patterns, and then I calculate the correlation coefficients from the 2 signals, and we group pair all the lower extremity muscles. And so one of our ideas here, the females may contract more quadriceps rather than hamstring muscles. That's why they might have more strain of the ACL because of the anatomical insertion. So, but compared to the male counterparts, so males got a co-contraction between quadriceps and hamstring, but maybe females are more hamstring and the quadriceps activation. So those are the idea, and that's why I look at the co-contraction patterns. So also I look at the timing issues from onset to the peak of the EMG, and this is basic information about the time of testing over the cycle. Look at the hormonal level, it increases, and also it increases gradually. And also we found some increase of major laxity using some machine, and it's very small, but 4 5 millimeters increases. And let's look at the data. We look at the muscle activation patterns, onset and co-contraction. But when you look at those variables by the menstrual phase 1 to 3, there is not much going on. It's very similar there, but so we have to look at the more carefully. So, but let's say like we have a 26 subject, and maybe more than half subject. Maybe like a 14 subject, they are showing relatively high visual laxity compared to other phase. But the summer, they are different. They might increase visual laxity at a different phase. So it's kind of it's hard to control. So later I regrouped all the data based on their relative visual laxity, high, medium, low. Then we compare all the biomechanical variables depending on their relative visual laxity rather than phase, because there are individual differences even we see the general increase in laxity. Then this is our first finding. So this is a high laxity, so which means that when subject has a laxogen, it is rolling moment impulse, they increase loading during this movement. It's very interesting. It was a kind of first finding in the literature. Laxity increases during loading. Then I look at the muscle